Electrical mobilities of electrolyte solutions. Consider a very simple cell which is composed of electrolyte solution, and two electrodes are dipped in it which are connected with a battery. So when a potential difference is applied across the two electrodes, the ionic species present in the electrolyte solution will move towards their respective electrode as shown here. So practically due to the movement of these electrical or ionic species generate the current which cannot be measured using this simple cell. For this purpose this kind of assembly is used, which is a kind of Wheatstone bridge cell. So here we have conductivity cell in which we can apply the potential, and also we can measure the current. At particular applied potential or the voltage, the current in an electrolyte solution is the sum of the currents carried by the individual ions. So now consider a solution with only two kinds of ions: positive ions with charge Z plus E and negative ions with charge Z minus E, where E is the elementary charge. So let's discuss the movement of the positive charges. When a potential difference is applied to the electrodes, the cation's field and electric field is shown here, that is E. So this electric field accelerates these positively charged ions. As these ions are present in the electrolyte solution, so there is a solvent which poses an internal frictional force present between the different layers of the solvent. The viscous frictional force exerted by the solvent on the ions is proportional to the speed of the ions and opposes their motion, and this frictional force increases to prevent the motion of the ions towards the electrode due to the applied electric field, and this force increases as the ions are accelerated. When enough electric field is applied that the viscous force balances the electric field force, and the cations are no longer accelerated and travel at a constant speed known as drift speed. Now consider there be n plus cations in the solution, and in time t, that is the difference, the cations move a distance. So for distance, that is given as drift speed into time duration. So in time delta t, the cations move a distance given as this equation, that is the between these two electrodes, and all cations within this distance from the this one electrode will reach the other electrode, or from here to here within time t del t. So the all cations, or the number of cations within this distance of the electrode, is given as and the number of cations within this distance of electrode is number of cations will be equal to the distance of all cations over the length. It is the separation between the two electrodes. Each cation is carrying a charge Z plus E. So overall positive charge is written as dq plus, so which is crossing a plane that is shown here parallel to the electrodes in time dt. So the total positive charge of this condition will be equal to that is the difference in charge which is moved from one electrode to the other with the application of the applied potential, and that is moved with drift speed in respective time duration, that is given as the charge on the positive cation into drift speed and the total number of positive ions, drift speed into time, that is the distance, over length, which is the separation between two electrodes. So this term have unit of coulomb, that is coming from this elementary charge. So here this one is the unit, and this equation is giving the total positive charge crossing a plane parallel to electrode. Plane parallel to electrodes. So here we have this plane which have been highlighted in blue as area. So the current density due to the positive ions is equal to the current due to the positive ions over area between the two separation of these two electrodes. And as we know that the current is the charge movement with respect to time. So current density have been redefined in terms of the total charge. So let's call this equation as 1, and so by comparing equation 1 and 2 we can write the current density due to the positive charge is equal to charge on each ion into drift speed and total number of charges over volume. Here volume is actually equal to the surface area, area between the two electrodes and into the separation between the electrodes. So here V is the solution volume that is present between the two electrodes. So here we get equation number 3, and similarly the anions will contribute to the current density that we written as, again, the charge on the elementary ion, the drift speed of the negative charges, total number of negative charges over volume. So here we have equation number 4. So these signs are showing the drift speed due to the either positive or the negative charges, but the magnitude of these two terms is actually a positive value, that is the speed of the charges. So these two values are considered positive. And in equation 3 we can see that the n plus is the number of positively charged ions. So we can write the number of ions is actually equal to the number of moles of the positively charged ions into the Avogadro's number. So we can write the equation number 3 as where the charge into Avogadro's number is equal to the Faraday's constant, whereas the number of moles over volume is equal to the concentration, that is for positively charged ions. So again we can redefine this equation as current density generated due to the positively charged ions will be equal to the Faraday's constant into drift speed and the molar concentration. Similarly, we can write this same equation for the negatively charged ions, that is written as equation, we can write equation number 5 and equation number 6. So the total current density generated by the cell is the sum of the current density generated due to the positively charged ions and due to the negatively charged ions is equal to the. So here we need to take the magnitude of the valency on the negatively charged ion. And this equation holds good for the two kinds of charges which are almost similar. For several kind of ions present in the solution, the current density due to ion labeled as B will be equal to drift velocity of that ion and the concentration. So this equation holds for the current density due to ion B, and if we have a number of ions, so the total current density will be equal to the sum of the current densities produced by the ion B. So here we have the total current density That's the valency on the ion, Faraday's constant, drift speed, and the molar concentration. So here we have equation 8. So if we have particular ion B, it will have contribution to the overall current density is shown as equation number 8. So here we can see that the current density generated by the ion B is proportional to the molar charge, that is the, from here if we can see that molar charge in and drift speed, as well as the concentration, that is the molar concentration of this charge or the ionic species. The drift speed is proportional to the strength of electric field greater the electric field strength, greater will be the drift velocity or the speed, and it is also depend on the type of ion and solvent used. Temperature, pressure, and the most important is the concentration of all types of ions available in the solution. Since we know that the current density is equal to the product of conductivity and the electric field strength, so according to equation 8 we can write the conductivity of solution, that is equal to the sum of the molar charge into drift speed and concentration over electric field strength. So here we get equation number 9. So now consider a constant concentration of an electrolyte solution. So for this kind of solution, the concentration value is fixed. So experimentally this solution is obeying Ohm's law. It means that the solution is independent of the applied electric field, as electric field over the current will give a constant factor known as resistance, which is expressed in terms of the conductivity. So the conductivity of the solution containing the fixed concentration of the electrolyte will have a constant value which is independent of the applied electric field, as the electric field will be proportional to the current with constant value of resistance that directly give the constant value of the conductivity. it means that conductivity is independent of applied field, which means that for a fixed concentration in the solution, each ratio of drift speed over applied electric field is equal to the constant, that is almost equal, that is characteristic of the ion B but independent of the electric field strength E. We call this constant as electric mobility of ion B. So in equation 9, this term or the factor is actually a constant value for a fixed concentration. So the drift speed now can be expressed in terms of electric mobility of ion B. So the preceding expression for the conductivity as given equation 9 will become the electrical conductivity sum of the molar charge. This term is molar charge and electric mobility and molar concentration. So that is equal to the sum of the conductivities due to the species B. So where Kb is the concentration of ion B to the conductivity for a solution with only two kinds of ion. We have equation that is given as again the molar charge into electric mobility and molar concentration. Now here we need to consider a point that each small portion of the conducting solution must remain electrically neutral. So for neutrality required that the charges, that is the concentration of the positively charged ion must be equal to the concentration of the negatively charged ions. So which means that the total charge on a small portion of the solution must be electrically neutral, so they are combinedly making the solution as neutral, but any small departure from the electrical neutrality will lead to the huge electrical field. So we can write this equation 10 for the conductivity for charged species B, and this one is for two kinds of ion, as the overall small portions of the solution must be electrically neutral. So the overall equation 11 can be defined in terms of common terms, that is due to the electrical neutrality, the molar charge is the constant factor as well as the concentration, but the electric mobility of the oppositely charged ions is different. So the current density can be expressed as, when taking the two terms as common, as by making the solution as electrically neutral. So we have current density that is equal to the equation, and we can say that this equation is 12, and here we have equation 13. So again, molar charge, molar concentration, and we have sum of the electric mobility of ions B for positively charged species and the negatively charged species.